So, this is the second part of this course. The second part of this course, which is the shortest one in the three, is in between the study of the cycles and the study of the components. We are there, in fact, studying the engine, the aero engine as a whole, from the point of view of, let's say, its performance globally, in order to understand the engine in a complete way, but considering the influence of the different components. So, in link with the first part, what we will see here is, let's say, applicable to all engine types. And we consider all engines of the first part, considering then globally the full engine. And in link with the third part that we will start next week, I'm discussing, in fact, the influence of the different components that we will see in the study of the components on this global engine. And this is what we will do in this intermediate part of the course, in the second part between part 1 and part 2, or part 1 and part 3, if you want. We could call that, in fact, a part 1-2 instead of a part 2, because it's really making the link between the study of the cycles in part 1 and the study of the components in part 3. Then you call this part part 2, or if you call the components part 2, we have this part which is 1/2, which is making really the link between the two parts. So we will introduce the influence of the different components inside a global study of the engine. And we will make that based on what is called the reduced parameters. Reduced parameters, this is something that you have seen already in the study of pumps, in the study of compressors, in the study of turbines. This is using what is called reduced parameters. What is the objective of these reduced parameters? This is related with the theory of Vashi-Buckingham. And you can express this theory of Vashi-Buckingham or Buckingham P, it depends on the authors or they are calling this theory, but you can interpret this theory in different ways. In this course, very practically, we will explain it like this. Until now, we have always considered the global engine as an engine, if we call turboprop or turbofan or afterburning or turbojet, whatever, we know that we can express the global parameters as a thrust and as a TSFC. We have seen even in the case of the turboprop, we can define an equivalent TSFC and an equivalent thrust if we want. And we have always said that these performance parameters were functions, 1 and 2, of 4 parameters that we have called the working parameters. We can express them in different ways, like PA, P atmospheric, TA, T atmospheric, the flight speed, VA, and the PLA. And we can also define other 4 parameters, whatever. We could say the temperature of the oil in the second bearing. It is also a parameter that we could put there. Whatever the parameters you want, you can choose them. Which one you want, you can put them there. You have just to have 4 independent parameters. And very often we will more speak in altitude. This is the pressure altitude that we call altitude. The delta T compared to ISA, which is atmospheric temperature, OAT, whatever you want to call it. Very often we will more speak in Mach number. And here we will speak in a parameter that is represented by, or that is representing the PLA. Very often we will call this parameter, we will use as this parameter the rotational speed. Is it N1? Is it N2? Is it something else? I don't know, but a rotational speed. And we have, of course, a certain difficulty in studying this because we have introduced, in fact, 4, let's call them working parameter, and this is maybe a bit too much. I have also sometimes indicated that the parameter that we could call, that we could use there for the PLA is also the mass flow rate. This is also related to the position of the throttle, because when you change the position of the throttle, everything is changing. One of them is certainly the mass flow rate. But it's complicated. This is making the problem very complex, difficult to interpret, difficult to understand. So many parameters changing independently. Are we not able to simplify the situation? And mainly, there are 2 parameters here that are certainly a problem. These are these 2 parameters. These 2, or if you want, you can call them also PATA. Because if you want to express these parameters, or if you want to measure them on a test bed, you will need to change PA. How can you change PA? You can move your test bed from here to the Alps, for example. It's possible. Not so easy. But mainly you will have TA. TA in the winter, TA is not 30 or 35 Celsius. And in the summer, TA is not minus 5 Celsius. So these parameters are difficult to take care of. And when you express the problem like this, of course, in aeronautics, everybody is directly thinking to reduce parameters. Because this is what we did already in the study of the turbines and the study of the compressors. I remind you that in the study of the compressors, we were using as performance parameters, of course, not the thrust, of course, not the TSFC. We were using there the pressure ratio, which is PT out divided by PT in, PT out divided by PT in function of the mass flow rate, okay? And we add as another parameter the rotational speed. It makes the curves like this, with a rotational speed that is increasing. Of course, there is a limit that we will need to discuss later on, which is the surge line. I'm not insisting on that as of today. And this curve must be taken for each couple PA-TA. Also, for every gamma and every Reynolds number or viscosity, this is, let's say, also to be considered, but normally we work with air, normally we are at high altitude, so the Reynolds number is, let's say, high enough and not too small, and very often these 2 parameters are considered but put a bit on the side. Of course, there are exceptional cases or special cases where you will need to consider gamma and the Reynolds number, but very often in the compressor it's not the case. And how have we solved this solution? We have introduced the reduced parameters, considering the theory of Vashi-Buckingham, by introducing a way to define these reduced parameters. And we have solved the problem by replacing this parameter by what we have called the m dot reduced. That is equal to m dot multiplied by the square root of the TT in divided by the PT in instead of this parameter. And we have replaced the rotational speed by a reduced rotational speed that we have called n divided by the square root of TT in. And when you do that, you do not need to consider anymore the PATA. And from a situation where you have a book of compressor maps, each sheet at a different couple PATA, you are coming from a book with I don't know how many sheets to one sheet. Just one sheet, which is one single compressor map with this parameter and this parameter. I remind you also that we have introduced at a certain moment something else than the reduced parameter. This is what we have called the corrected, CORR, for example, as an acronym. That is not equal anymore to this one, but where we have introduced TT in and PT in, let's say, reduced by their standard values, 288.15 Kelvin, and here 101, 325 Pascal, 225 Pascal. And here, that we have replaced by N corrected, that is equal to N divided by the square root of TT in divided by 288.15. Of course, this expressed in Kelvin. This expressed in Kelvin and this expressed in Pascal. Why have we done this? This is because M reduced as a very strange unit. M corrected as the same unit as M dot. And N corrected as the same unit as N. So you are in the world of the reduced variables that we call corrected variables. And these reduced variables, it's a bit strange, but they have units that are the same unit as what we call the physical variables. These variables are called physical variables because PA, you can measure that with a physical instrument. TA, you can measure that with a physical instrument. VA also, and PLA also. And also the rotational speed, and also the Mach number, and also the altitude, and also the delta T compared to ISA. You can measure all these parameters physically. You can also measure the thrust with a load sensor. You can measure the TSFC with a load sensor and a flow meter to measure the fuel flow. So these are physical parameters, and we switch from the world of the physical parameters to the world of the reduced or corrected parameters without taking with us the influence of the atmosphere. And so, being able to consider, being able to introduce that, we think about, can we do the same for our engines? This is the basic principle. And we will do that considering reduced parameters or corrected parameters, but very often I'm not making so much the difference. It's just a question of name, because it's the same philosophy in the reduced and in the corrected parameters, except that you have the good and the adequate